We are going to consider one of the historically how Galois theory really arose, which is from the efforts to solve polynomial equations for their roots. So for example, recall if you have a quadratic equation, then we have a formula for its roots. So ax square, so let's assume it's monic, x square plus bx plus c equal to 0. The roots are given by minus b plus minus by 2. Now similar formulas were known for both degree 3 and degree 4 equations. Okay, and the formulas always involved some closed form expression like this. So maybe it was things like something which involved cube roots or square roots or fourth roots and so on. And often they were rather complicated such expressions, but nevertheless there was some closed form expression that people had managed to work out. So among the famous names associated to the cubic equation is Cardano. So there is the Cardano solution to the cubic polynomial. So degree 3 polynomial, degree 4 polynomial, and of course that brings the natural question up, which is, can one do the same thing for all polynomials of all degrees? And Galois sort of considered this problem, as did some people before him, but Galois theory really arose from his efforts to understand the solvability of the roots for a general polynomial. And it turns out that degree 5 polynomial, a general one, some of them can be solved, but you can always find degree 5 polynomials whose roots cannot be expressed in such forms. You cannot find a formula for the roots. Okay, so what we are going to do over the course of the next few videos is to try and see how this is proved. Okay, now let me just define some of the notions that we will need. Now given a polynomial, so here now we are going to always look at the base field q, and so we know that given any polynomial with coefficients in q, it definitely has roots in the complex numbers. So we'll sort of keep looking at q and c throughout. Okay, I'm not going to look at any other fields really. Okay, now definition: given a polynomial, given polynomial f with coefficients in q, we say that the Galois group of f. Okay, so this is the definition: the Galois group of f, and I'll let me give it a name, gal of f, is the following. It's just the Galois group, or the group of automorphisms of k over q, where k is the splitting field of f. Okay, so look at the splitting field. Because it's a splitting field, it's normal. Q is of characteristic 0, so this is separable, and so it's a Galois extension. So you've got this Galois group, the group of automorphisms, and we call that the Galois group of f. Okay, so for example, if so we have seen many such examples before. If it's a quadratic x square minus 2, then the Galois group of this polynomial has cardinality 2, so it's just isomorphic to the cyclic group. If I have x to the n minus 1, then the splitting field is the cyclotomic field of the nth roots of unity, and we have seen that the Galois group of the cyclotomic extension is the, well, you take the ring Z mod nz and you look at the units in that ring, okay, the elements which have multiplicative inverses. And we have seen, so this cardinality is phi of n and so on, Euler's torsion function. Okay, and so here's the eventual theorem that we are going to go towards. Okay, let me state it up front, and there are many intermediate steps which we will take up one by one. So given a polynomial with coefficients in q has degree 5, and if its Galois group is isomorphic to either the symmetric group S5 or the alternating group A5, okay, remember that's the set of even permutations, then the roots of f cannot be expressed as radicals. Okay, so the keyword here is radicals. We sort of know what that means in the quadratic and cubic cases. So radicals are things like this, taking some nth roots of other expressions. So what is an example of what is a radical expression? So here is a radical expression in terms of radicals. Okay, I'll give you an example. So let's do something complicated. I can take square root 91 plus 4, something like that, maybe plus square root of cube root of 4 plus cube root of maybe the 7th root of 9, and so on. So you can imagine what I mean. So I can have many layers of nesting, meaning I can take the square root of the cube root of some expression and so on and so forth. Okay, so any such thing is what we would like to mean by a radical expression or an expression in terms of radicals. So what this theorem says is that you cannot get a formula for the roots in of this form, okay, which we are able to do for quadratic, cubic and the quartic equations. Okay, so sorry, I called them quadratic again. This is what's called quartic, which is degree 4. Okay, now let's see how to formalize this a little bit better. So definition, what does it mean to take radicals? So a simple radical extension. So I'm going to define what is meant by a simple radical extension. Is an extension of the following form, is an extension of the form, okay, I have some base field and I have an extension f which is obtained by adjoining just a single element alpha to the base field, such that what property is alpha? Some power of alpha belongs to the field. Okay, so for some n greater than or equal to 1. Okay, in other words, i.e. alpha satisfies the polynomial, what polynomial does satisfy x to the n minus beta equal to 0, okay, for some beta which belongs to the base field. Okay, so it's another way of saying you take some element of the base field and you adjoin some nth root of that element. Okay, so that's like what we are doing in these examples, right? So we sort of take some element of your base field, say maybe this is your element of the base field, then you're trying to take the cube root of that element. Okay, of course this element of the base field itself is obtained as, you first take root 5, you adjoin square root of 5 to the rational numbers, you get some field. Now to that field you adjoin another element, the 7th root of 9, and you get another further element and so on. So we are not just doing radicals in one step. So this is what we have defined so far, is what it means to just do a one-step radical. More generally, we have a definition. So an element alpha in C, a complex number, is said to be expressible in terms of radicals. You say it is expressible in terms of radicals if there exists a tower of simple radical extensions. Okay, so there should be a tower of the following kind, that I start with the rational numbers, I'll call that k0, there should be k1, k2, such a tower such that each ki over ki minus 1 is a simple radical extension. And alpha is in the topmost guy, alpha belongs to kr. Okay, so when I say each of this, I mean for I equals 1 to r. Okay, so this is the formal way of encapsulating the idea that you keep doing multiple nth roots, you keep taking multiple nth roots. Okay, now observe, just a quick aside, that this is very reminiscent of what we have seen already for constructible elements. Okay, so this is formally similar to the definition of constructible elements, to the what we call constructible numbers. Right, there we said we had to start with q and keep doing, you know, quadratic extensions, and a real number there was said to be constructible if it can be realized as part of the topmost extension in a tower where, you know, each successive thing is quadratic. Now here we don't demand it's quadratic, instead we say each of them should be a radical extension. Okay, it should be obtained by adjoining some nth root, need not be a square root. So recall, quadratic extensions are always realizable as adjoining a square root of some element from the base field. In this sense, this is a generalization. You can adjoin any nth root. Okay, good. Now what's the key fact that one needs to know about this? So that's the following proposition. So let n be at least 2. I mean, adjoining the n equals 1th root of an element doesn't give you anything new. Okay. Now let f be a subfield of C containing all nth roots of unity. Okay, containing all nth roots of unity. So e to the 2 pi I by n and its square, cube, and so on. Now if alpha in C is such that its nth power belongs to f, then the extension, so I have f and I adjoin alpha to it. The claim is that this extension is actually Galois. Okay, further with cyclic Galois group. Okay, so this is the key proposition. So observe, this is a simple radical extension, right? So what this means, in other words, i.e. simple radical extensions, and I'm only talking about subfields of C here. So simple radical extensions have cyclic are Galois and have cyclic Galois groups. Okay, so have Galois. That's just a quick way of remembering what this says. Okay, so let's prove this. So first let's show that this is actually a Galois extension. Proof. So what are we doing here? To show that f alpha over f is Galois, we need to show that this is the splitting field, for example, of a collection of polynomials. So here it's very easy to see what polynomial we are talking about. Let's just take the polynomial x to the n minus beta. Okay. Observe that, so what are the roots of this equation? So the roots of this polynomial, one root we know, which is alpha itself, but then the other roots are just alpha multiplied by the various nth roots of unity, alpha zeta to the n minus 1, where zeta is just this nth root of unity. Okay, so these are the roots, but observe, we made an assumption that f, the base field, already contains zeta, zeta square, zeta cubed, and so on. Okay, so therefore observe that if I take f and I just adjoin f alpha to it, so maybe I should say this first, if I take f and adjoin alpha to it, that's the same as adjoining alpha zeta square and all the other roots as well, because zeta is already in f, since zeta and its powers are already in the base field by assumption. Okay, so adjoining just alpha will automatically give you all the nth roots, I mean all the n roots of that polynomial. Okay, so what does that mean? That just tells you that f alpha is actually just a splitting field. Right, this is the definition, right? Splitting field should be the field generated by the roots of that polynomial over the base field. So this is the splitting field of this polynomial over the base field. Therefore, it's Galois. Okay, here characteristic 0, so separability is not, it comes for free. So it's normal, therefore Galois in this case. Okay, good. Now what about the Galois group? Where is the cyclicity of the Galois group going to come from? So recall, we have looked at this in the various examples and so on. What are the possibilities for an element of the Galois group? So take an element now, sigma, in the Galois group of this extension. Okay, so as always, it's determined by what it does to this generator. Okay, so if I know what psi does to alpha, so this uniquely determines, if I specify this uniquely determines psi. Right, you can work out what the images of the other elements are. Now, what can psi alpha be? Okay, again, if you look back on our problems that we did, so what this says is that psi alpha can only be one of the roots of its minimal polynomial. In particular, here I don't quite know maybe what the minimal polynomial is. I don't know that this is irreducible, the polynomial I chose, little fx. But whatever it is, since alpha is a root of f of x, psi alpha must also be a root of f of x. So what are my possibilities? I already know what they are. It's only one of these. Okay, so now point is, okay, so let's just define a map. Let's take the map. So I'm just going to take the nth roots of unity. Okay, 1 zeta square, zeta to the n minus 1. Okay, so this is, I'm calling this gamma n, the nth roots of unity. These form a group under multiplication. Okay, so what we'll now do is we will define a group homomorphism between these two groups. So this is a group under multiplication. Okay, what's the map? Well, we just said take any psi, it's uniquely determined by what it does to alpha, right? So, and what can psi do to alpha? Psi has to map alpha to an element of the form alpha into some power of zeta, right? It should look like alpha zeta power k for some k between 0 and n minus 1. So now what you do is you just map it to that k, that's all. So psi will map to zeta power k, where what is k? K is that element such that psi alpha is alpha zeta power k. Okay, this is the definition. Or if you wish to have something which looks a little slicker, you just say psi maps to psi of alpha divided by alpha. That's really what this map is. Okay, good. Now we just have to check a few things. The claim is that this map is an injective group homomorphism. Okay, so claim this map is an injective group homomorphism So let's check the injectivity first. If something maps to the identity, so first I will check injectivity. If psi maps alpha, so if psi maps to the identity of the group gamma n, what does that mean? It means that psi of alpha is alpha, right? Okay, if psi maps to 1, it means that psi of alpha is alpha. Therefore, that automatically means that psi must just be the identity on the entire field f of alpha, because psi is already identity on f and psi of alpha is also alpha, so psi must be identity. So that shows that this is an injective map definitely. But let's check that it's a group homomorphism. Now group homomorphism is, well, suppose psi maps to zeta power k. I take another map psi prime which maps to zeta power k prime. Psi and psi prime are elements of the Galois group alpha over f. Then what can I conclude? So what does this mean? In other words, psi of alpha is alpha zeta power k, psi prime of alpha Okay, so let's compute what the composition maps to, psi composition psi prime. Well, its value on alpha by definition is, I first apply psi prime is zeta power k prime, which is psi of alpha into psi of zeta power k prime. Okay. Now, on the other hand, well, I know something more. I know that psi of alpha is alpha times zeta power k, and psi on zeta power k prime, observe zeta power k prime by definition, this element here was assumed to be in the base field. Okay, and psi acts as identity on the base field, so this just maps it back to itself. It does nothing to it. Psi of zeta power k prime is zeta power k prime. So the final answer therefore is alpha zeta power k plus k prime, which means that psi composition psi prime is going to be mapped to zeta power k plus k prime. Okay, which means it's a group homomorphism, because that's the group law on the right hand side. So we have managed to prove both parts, that it's an injective group homomorphism, which means that the Galois group is isomorphic. So the Galois group, see, there is an injective map to an abelian group. So observe that gamma n, the multiplicative group of the roots of unity, it's after all an abelian group there. Okay, and it's in fact cyclic. So this is actually a cyclic group. This is cyclic, generated by zeta, right? Powers of zeta give you everything. So this is really a subgroup of an abelian group. It's isomorphic to a subgroup of a cyclic group. So therefore this is also cyclic. Therefore aught of f alpha over f, you can think of it as it's isomorphic to a subgroup of a cyclic group, and the only subgroups of cyclic groups are cyclic. Therefore it is already cyclic. Okay, so that's the end of the proof. So what we have managed to show is that simple radical extensions are necessarily Galois and have cyclic Galois groups. And now the key thing about a tower of extensions, or about expressing numbers in terms of radicals. So here's the proposition: if you can express alpha, if an element alpha is expressible in terms of radicals, then what it means is that then there exists, the proposition says there exists a tower, okay, as follows: Q, it's called Q is L0, L1, L2, Lr, such that alpha belongs to the last fellow Lr, and each Li by Li minus 1 is Galois with an abelian Galois group. Okay, so you might wonder that, didn't we prove something more? Didn't we already say that every simple radical extension is cyclic? Well, we did. That's exactly what the earlier proposition said, that the simple radical extension f alpha over f has cyclic Galois group, but we made an assumption that f contains all the nth roots of unity. Okay, so now we are trying to state it without that assumption, and so there's just one little step that we need to do, which is we have to adjoin the nth roots of unity to our initial field Q. And once you do that, then everything works the same way, and that one step is what's going to give you an abelian group. So you can actually in fact say there's one guy which is abelian, the rest are cyclic, and so on, but for us abelian is all that will be required for our later arguments. Okay, so proof: by definition of expressibility in terms of radicals, what we know is there exists a tower Q equals, so I'll now write a tower like this: K0 K1 KR with alpha belonging to KR and each extension is a simple radical, and each ki by ki minus 1 is a simple radical extension. Okay. Now the point is, if instead of Q we had also a field which had all the nth roots of unity, then we can have concluded that these simple radical extensions are have cyclic roots. So what we will do is we will just adjoin those nth roots. Okay. So let's assume that each ki is just, you get it from ki minus 1 by adjoining some nth root, right, some alpha I, where let's say alpha I to the ni, it's the nth root of some element in ki minus 1. Okay, for some ni's are, you can assume they're all at least 2. Okay, so you get each successive step by adjoining some nth root of an element of the previous field to that field. Okay, so suppose this is the case. So I have these numbers ni, I know all of them, so I will just take their product. Okay, and what I will do is I will adjoin. So now consider, so I want to adjoin all the nth roots of unity. I can do it in one step by just adjoining the nth root of unity, capital nth root. Okay, so let's do the following. Let's take the cyclotomic extension q zeta, where zeta is e to the 2 pi I by capital N. Observe that if you have this is the capital nth root of unity, but this field also contains all the nth roots of unity. Okay, so this is a cyclotomic extension. This is a cyclotomic field, and further it contains all nth roots of unity, right, because capital N is a multiple of ni for all I. Okay, now what does that mean? Well, that means now that I can, instead of this tower that I had, k0, k1, kr, I'll just construct a somewhat larger tower. Okay, so now define a new tower as follows. Let's define Li as, so this is instead of ki minus 1. So let's do it in steps maybe. So I had q k0 containing k1 is, I adjoined alpha 1 to it, then to k1 I adjoined alpha 2. Okay, so this I called as k2 and so on. So I keep adjoining successive elements. Now let's just define L0 to be q. So okay, let's define L0 maybe to be q of zeta. Okay, and now let's say L0 is contained in, so maybe we shouldn't call this as L0. So this is one additional step that I need. So let's say I have, so instead of the tower q alpha 1, q alpha 1, alpha 2 and so on, this was the original tower that we had. Now we will define a new tower in which we will also adjoin that zeta. Okay, so now instead of q, start with a larger field q zeta, and to q zeta you adjoin alpha 1, to q zeta alpha 1 you adjoin alpha 2 and so on. So consider this new tower. Okay, and of course q is contained in q zeta. Okay, now I'll call these as my L's. This is L0, L1, L2 and so on. Okay, now this last step is some q of alpha 1, alpha 2, alpha r. This is q of zeta comma alpha 1, alpha 2, alpha r. So this guy is well, unfortunately, because of the way my numbering went, this is LR plus 1 rather than LR. Okay, but doesn't matter. My key point finally is that I can construct a new tower in which all the nth roots of unity are guaranteed to exist in the base field. They all exist in L1 itself. Okay, now we just use our previous proposition. Okay, by our previous proposition, observe that each step is a simple radical extension. So observe that each Li over Li minus 1 is a simple radical extension. Okay, and further, Li minus 1 contains all the nth roots of unity, definitely. Okay, so contains all the required roots of unity. So maybe we should just be slightly more careful here. So Li over Li minus 1, what is it really? Li is Li minus 1 adjoined. So there's a slight numbering thing here. L2 is obtained by adjoining alpha 1. Okay, so it's Li minus 1 adjoined alpha I minus 1 now. Okay, so this is for I at least 2. Okay, now so what do I know? So this is simple radical extension, and the base field, which is Li minus 1, contains the n I minus 1th roots of unity, which is what I need for my earlier proposition. Okay, so these hypotheses are satisfied of our earlier proposition. So we conclude from our previous proposition that Li over Li minus 1 is Galois with a cyclic Galois group. Okay, and cyclic is of course abelian. Okay, now this only deals with extensions from the second stage onwards, that is, this has cyclic Galois group, this has cyclic Galois group, and so on. But we still have to worry about the very first step in the tower, L1 over L0. But recall, L1 over L0 is just a cyclotomic extension, right? And we know what the group of a cyclotomic extension is. So this is of course just a cyclotomic extension, which we have studied. Therefore it is Galois, we know that, with, well, what's the Galois group? It's Z mod, whatever it is, capital N Z, the group of units of that ring. So therefore it's definitely abelian. Okay, so the first step is some abelian group, the remaining steps are definitely cyclic in fact. Okay, so that proves the theorem.